Hello, today we're going to talk about reductions and oxidations. And in order to fully understand what's happening in each one of these reactions, we're going to have to revisit the idea of organic redox. And you may recall from our first lecture that in order to determine the oxidation of a carbon atom, you just have to count the elements that are directly bound to that carbon. And if carbon is bound to another carbon, then there is no actual redox event for that particular bond because they have the same electronegativity, right? So you will neither reduce nor oxidize another carbon with a second carbon. But if what's bound to the carbon is less electronegative than carbon, then it will reduce it. And the typical example is hydrogen. Hydrogen is less electronegative than carbon, so it will reduce it. And the idea is that for every single bond that you have present, or every single line that you have present, if that's a hydrogen, a CH bond, then you will count that as a -1 oxidation state on the carbon. Now, on the other hand, if what you have bound to carbon is a more electronegative element than the carbon itself, then you will be withdrawing electron density away from the carbon and you will oxidize your carbon. And for every line that is present to a more electronegative element, the carbon is going to have a +1 charge in association with that bond. So this is what you have to remember. As far as reduction goes, you're going to have a -1 for every single bond that you have to a less electronegative element. And if you are bound to a more electronegative element than carbon, you will have a +1 for every single bond to that element that is more electronegative. So let's take a look at some of the reactions that we've seen in the past. These are the addition reactions that we talked about previously. And if you look at the substrate, the organic substrate, and then look at the organic products, what you're going to find out is that the alkene right here, where the chemistry is happening, if you look at it from the point of view of redox, you can see that this carbon is bound to only other carbons, carbon, carbon, and carbon. So this carbon is unaffected in terms of its redox properties, so it's basically got an oxidation state of 0. But the carbon over here has a hydrogen bound to it, which will make it -1. But at the same time, this very carbon is bound to a chlorine, which will make it +1. So -1 plus 1 will make it neutral. And if you look at the rest of the stuff right here, you can see that your methyl groups with 3 hydrogens are going to be -3. Carbon with 2 hydrogens, -2. But the alkene here is where the bulk of the process is taking place, because by the time you add HCl to it, well, notice that the carbon over here, the carbon over here has an extra chlorine that has completed the process. And if you look at the oxidation state, this carbon is bound to carbon, 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 but now it has a chlorine, so now this is +1. And the carbon over here has now 2 hydrogens and only 1 chlorine. 2 hydrogens will give you a -2 charge on the carbon, 1 chlorine will give you a +1, -2 plus 1 will be -1. And so what you're seeing is that one of the carbons has been oxidized, specifically the one on the left side, but the other one has been reduced from the point of view of the original product. So you can actually have these effects taking place when you do reactions. Not all the carbons have to be oxidized and not all the carbons have to be reduced. You could have some of them oxidizing, some of them reducing. Here's another example. We take this trans alkene with chlorine and fluorine. We carry out the addition. First of all, looking at the alkene right here, this carbon has a hydrogen bound to it, so it's -1 in oxidation state, and likewise the carbon over here is also got a hydrogen bound to it, so the oxidation states will be -1. By the time we get to the products, after the addition process is taking place, this carbon has a hydrogen bound to it, but it also has a fluorine. Fluorine gives the carbon a +1 charge, the hydrogen will give it a -1 charge, so now this is neutral. And by the same logic, the carbon over here has a hydrogen bound to it, which gives it a -1 charge, but the chlorine gives it a +1 charge. So overall, these carbons are neutral. And so what's happening, if you look at the reactant side, is that both of them went from -1 to 0. So this is a full-on oxidation, right? Nothing here is, doing half oxidation, half reduction. All of the carbons are being oxidized from the point of view of the alkene. Okay, and then your addition reaction with dibromine, which gives you dibromo molecule with anti-configuration. It's a similar idea. The carbon here on the left is -1 because it has a hydrogen bound to it. The carbon over here is a -2 because it has two hydrogens bound to it. And over here, the carbon here on the left side has one hydrogen bound to it, but it also has a bromine, so it's overall neutral. And the carbon over here has two hydrogens, and it has one bromine. So two hydrogens is -2, one bromine is +1. So overall, that will give you a -1 charge. And if you compare it to what we had originally, we went from -1 to 0, that's an oxidation. We went from -2 to -1, that's also an oxidation. So this is full oxidation altogether. But when you look at hydrogenations, what you're gonna notice is that here we're adding hydrogen to the carbons, and hydrogens are less electronegative than carbon. So we start with an alkene that's -1 and -2 on those carbons as far as the oxidation state is concerned. But by the time we carry the hydrogenation, the carbon over here now has two hydrogens in total, whereas the one right here has three hydrogens in total. So now the charges have gone down to -2 and -3. And compared to the reactants, this is a full-on reduction. So hydrogenations are actual reductions, whereas your halogenations tend to be oxidations. Okay, let's take a look at one more example. This one is the oxymercuration, demercuration of an alkyne. And you may recall that when we react an alkyne via this method, initially we produce an alcohol that's directly bound to an alkene, and that undergoes tautomerization to produce a carbonyl compound. Since mercury will stick with the carbon that is less hindered, you end up placing the oxygen on the carbon that will be most hindered, right? And that means that you're going to end up with a ketone at the end of this process. So looking at this, you can see that the carbon over here for the internal alkyne is going to be neutral because it's bound to just carbons. The carbon here on the right side, on the other hand, is bound to one hydrogen, so that will be -1. By the time you carry the full-on oxidation, the addition of water via the oxymercuration, demercuration, you find out that the carbon here on the left side is now got a double connection to oxygen, and each one of those lines counts. So this is not a +1, but rather a +2 oxidation on carbon. Whereas the carbon on the right side has now three hydrogens bound to it, so it's got now a -3 charge. So here you are definitely, if you look at the carbon on the left side, you have undergone an oxidation, but for the carbon on the right side, you have decreased the charge, so this is now a reduction. So you get both things happening right here. And if you think about it, that is not all that surprising because you are adding a water equivalent to this molecule, which means that something is going to get oxygen, but the other carbon is going to get hydrogen. So you do have this oxidation reduction mix happening. Okay, so with that little intro, we are pretty much ready to begin talking about the oxidation and reduction reactions that form the basis for carbonyl and alcohol chemistry. But I'm going to save that until the next video. So I'll see you there.